On what game? You just never. Oh, yeah. Yeah.
Okay, we'll go ahead and get started. Continuing on with the aromaticity module. Our focus now is going to be on learning the reactions. The reactions themselves, I think, are quite straightforward. You're basically substituting a hydrogen on a benzene ring for some other group. So there's a couple of conditions. We learn how to get carbon or a heteroatom on there. And then, over the course of more likely Wednesday and next week, where it gets a little bit more difficult is once you have something on the ring and you want to do another reaction, of all the possible positions, where is the next reaction going to occur? And that really is dictated by the nature of the substituent. So resonance is the important thing here. The resonance forms will tell you exactly where it's going to go. And the reason we want to study that is, again, if you go onto like PubChem, which is the library maintained by the National Institutes of Health, you can search any drug structure. And if you find ones with aromatic rings, the substituents are in specific relationships to one another. If you move a group over one carbon, that's a totally different molecule. It will have totally different indication biologically. So we want to understand, how do we design these things in a rational way? We don't just want to mix stuff together and see what comes out. That's not the state of the art anymore. So how do we use what we know about functional groups and the fundamental things like resonance and induction to predict where these things will go and what are their effects? So as we go through this, we'll review some mass spec, IR, and NMR spectroscopy so that we can know by looking at the data what is our intuition telling us about symmetry. So really what we're focusing on is just benzene, although the reactions themselves, we saw all these other aromatic compounds. By and large, the conditions, or you could translate to them, but we're just focused on benzene for the rest of this module. So benzene has the MF of C6H6. And what we'll go over the next couple slides are monosubstituted benzenes. We've taken one hydrogen, replaced it with something else. This gives us a library of monosubstituted benzenes. And then we're going to learn reactions that make them. So I have on this slide here, EDG. What does that stand for? So electron donating, and then G is group. So again, a lot of these don't have IUPAC names, like the formal IUPAC names, so they're just referred to as these common names. And they may or may not give you an indication of what the substituent is. So for lack of a better way, you just got to memorize them, or you just Google it during the exam to see what the structure is. So what are we doing? It's the wrong color. Do red. So there is benzene. I've highlighted one H of the 6 equivalent hydrogens in red there. The reactions we're going to learn, we're going to substitute an H for something else. So this molecule with the methyl group is called toluene. Most people will pronounce it toluene. It's toluene. So benzene and toluene are typically used as organic solvents. They have some interesting smells. Anyone make, like, they're not terribly popular anymore, but these plastic model kits, like cars or airplanes, they come in like a thing and you got to snap the piece off, and then you glue them together. So the glue that's used has toluene in it. And if you look at the package, the state of California always has to put their things on stuff. So there's these, like, this chemical causes cancer or whatever. But so toluene is in there, and it kind of reacts with the plastic to weld it together. And it has a interesting smell. Like, if you're into it, you could kind of sniff it for a while and feel good about yourself. So we'll learn how to get carbon onto a benzene ring. The next one is called phenol. That's hydroxybenzene. And phenol has many different names. Phenol is the most common one. It's called carbolic acid and some other things as well. But it's used in, I don't want to say dermatology because that's like formal, but like face peels and stuff. Like a very dilute solution of phenol is used as like a face peel, and essentially it's not structurally altering skin, but what it's doing is just tightening it up. So people that get these face peels with phenol typically come out of the appointment with a very red-looking face because it's just tightening the skin. And that's, again, done to kind of minimize the look of aging. So we'll learn how to get oxygen onto a ring, and then from OH to the ether in anisole, you already know how to do that. That's an SN2 reaction. We can deprotonate the alcohol, treat it with a electrophile methyl iodide, and that will make an ether. So once we get sort of the extra substituent on there, there's a lot of other stuff you can do to that now side chain. Aminobenzene is called aniline. So there's a company called BASF. The A in that company name actually stands for aniline. That shows you the importance of that molecule throughout history. And really the modern dye industry, when we talked about color and dyeing things, a lot of those dyes have aniline as a substructure or like a monomer of the dye itself. And then lastly, halogenated benzenes. So I just gave up fluorobenzene here as an example, but any other halogen, we'll learn how to get on there. So to make these things, we have to start with benzene, and then we substitute off. But I have this comment here. Electron donating groups are more reactive than benzene itself. So as I said, we have C6H6. So if you want to put one of those groups on there, it doesn't matter which hydrogen gets substituted, because it's going to make a monosubstituted benzene. But now say you want to start with one of these and do a second substitution. Now the position will matter because you can end up with different relationships relative to that first group. And the reason it says these are more reactive than benzene is any mechanism will always have a nucleophile supplying electrons and an electrophile accepting them. In this mechanism, the benzene ring is the nucleophile. One of the pi bonds is supplying the electrons to form the new bond. So either through induction or resonance for the group shown, they're making the ring itself more electron rich. When you look at the atom that's directly bonded to the ring, we're going to call that the benzylic position. So these groups with heteroatoms that have lone pairs, so NO and halogen, the lone pair can be pushed into the ring. That makes the pi bonds electron rich to supply electrons. So I'm gonna draw some stuff on here that's gonna lead us down the intuition we need to develop. But it says, which of the following is not a resonance hybrid of phenol? We can back up and say, which one of these, as drawn, is phenol itself? So A is phenol. So remember that resonance is not the movement of atoms. So one of these is showing atoms moving. Which one is it? So D. C in phenol has OH, that H. In structure D, we've moved the H from the oxygen to a carbon. So that's not resonance. So A, B, and C are all hybrids. And again, the hybrid is really a representation of where electron density is or is not. So I'll draw these resonance forms by pushing arrows. Under the caveat here that the reactions we'll learn today are how we get things onto a benzene. What I'm showing you now is there's something there already. If we want to run a second reaction, where is it going to go? So our benzylic position has a lone pair. We can delocalize that into the ring. And again, for resonance, we have a lone pair. We have 1, 2, 3 atoms and the pi bond. So now, because the oxygen and the ring carbon don't have the normal bonding pattern, we're going to assign a plus and a minus. We have another system that we can show resonance for. And then one final hybrid. So as I've stated before, if you just start with benzene, you do a substitution, it doesn't matter where the group goes because all 6 hydrogens are equivalent. If we were starting with phenol and we wanted to predict where the next reaction would happen, wherever you see that lone pair in negative charge is telling you where the second reaction is going to occur. So in this resonance hybrid, it's right next door. So there was that OH group. So they're neighbors. This last one's also the same, neighbors. Then the middle one, if we count, 1, 2, 3, 4. So if you notice, where is the negative charge not located? In terms of the ring. So here we have a 1, 2. Here we have a 1, 4. Notice that the negative charge never ends up in the third position because the benzene ring is the nucleophile that's supplying the electrons. The reaction's going to favor where the electrons are. So there's no 1, 3. So any subsequent reactions we run with phenol, we can say that group is either going to go right next door, 1, 2, or it's going to go opposite, 1, 4. So the other main class is electron withdrawing groups, so EWG. Now these are substituents that make benzene, the ring, less reactive than benzene. Typically either because they have many electronegative elements at the benzylic position, or they have a heteroatom that's bearing a plus charge. And so that's going to pull electron density out of the ring, making the ring react slower. So over to the right, there's our benzene. If we substitute that H for a carbonyl that's embedded in an aldehyde, that's called benzaldehyde. If the carbonyl is a ketone, that's called acetophenone. We can have a carboxylic acid, that's benzoic acid. We can have a nitrile, benzonitrile. So on the prior slide, we had CH3 that was toluene. This is called trifluoromethylbenzene. So notice now the presence of those fluorines inverts the reactivity. And then NO2 is nitrobenzene. Just as a question, does anyone know what TNT stands for? No AC/DC fans in the crowd here.
The only reason I know what AC/DC is supernatural.
So TNT stands for trinitrotoluene. So there's toluene. And then if we shove in 3 nitro groups so it's symmetric, So TNT is made from toluene. And if you remember those resonance forms that we saw in the prior slide where that negative charge was, so the 1,2 and the 1,4. And so that is what is called a high energy material. Basically, it's used to blow stuff up. And it's interesting to think why that is. When you look at the composition of a molecule, the carbon, hydrogen, and then heteroatom, like percents that make up the molecular formula, as the carbon percent goes down and the percents of the heteroatoms go up, the bonds get weaker, and so you're able to break them easier. And through a degradation process, that will release energy. And so when an explosion happens, it's just energy being released. So TNT, dynamite, nitroglycerin, those are things that were developed basically for mining. There's some gold in there. I want to get it out, but I don't want to spend my life chiseling it. So I'm going to drill a hole, shove a stick of dynamite down there, explode it. That breaks the rocks. I can get the gold out. So on the next slide, we'll look at nitrobenzene and understand what its effect on the ring is for pulling electron density out. So this one says, which is not a resonance hybrid of nitrobenzene? So if we take NO2 and expand it into the Lewis dot structural formula, we'll see that the NO2 group, the N is positive, and it's balanced off by a negative on one of the oxygens. That positive charge is really what's dictating the reactivity of the ring, because it's going to take electron density out, form a double bond to the nitrogen, and then push a negative charge on the oxygen. So notice overall that the N in one of the O's is still negative. That balances off to 0. The other oxygen is now negative, and that means that the ring at that position is now positive. And what we'll find with the remaining resonance structures, that positive charge is now at the 1,2 or the 1,4 positions. And then the last one, we just migrate that plus charge again. So just like the electron donating, the withdrawing has a charge at 1,2 or 1,4. But the main difference is because the ring is the nucleophile, wherever there's not a deficiency is now where a second substituent will go. So we don't see the plus charge end up at the 3 position. So with these groups that are electron withdrawing, any subsequent reaction takes place at the 3 position. So the 2 different classes are said to direct differently. And again, that's based on, it's easiest to see with the resonance forms, but if they don't have resonance, then through induction, it will behave similarly. Any questions before we move on? So in the prior lecture, we said benzene does not undergo electrophilic addition. So that was when you had the electrophile with 2 elements adding across a pi bond in that 1-2 fashion. The reason it doesn't do that is because of the aromatic stability. It wants to retain that. And if we remove a pi bond, it's no longer aromatic, and then that affects the overall stability of the molecule. So the mechanism for benzene reactions is EAS. I always think of like electronic arts, sports games, beginning. Maybe they don't say it anymore, EAS. So electrophilic aromatic substitution. So just pay attention to that word substitution. An H is going to something else. So I'm not going to lead off with the mechanism other than to say that the ring itself is the nucleophile. That's the highest occupied molecular orbital, supplying electrons to the lowest unoccupied molecular orbital of the electrophile. So we want the benzene ring to be electron rich for things to be matched properly. So today we'll talk about primarily how do we get heteroatoms onto the ring. So H to nitrogens, oxygens, halogens, how do we do that? And then as over the course of these slides, we'll review some of the spectroscopy so that you know which conditions were used. The 3 classical ones are shown here. So halogenation, sulfonation, and nitration. Notice for halogenation, it's chlorine and bromine. Fluorine and iodine, due to their atomic properties, are typically not electrophilic enough, or they're too electrophilic that we can't control it. So these are the things that are tame enough that we can rationally produce one compound from a reaction. And so I have this nomenclature X2. So that would be your electrophile. But then we have this other thing in there, ALX3 or FEX3. Those are Lewis acids. So for example, aluminum trichloride, iron tribromide. The halogen itself is going to come from this. The Lewis acid is there to make that more electrophilic so that things are properly matched in terms of the orbital energies. So that will make a halogenated benzene. And we saw that halogens were electron donating groups. The next set of conditions is sulfonation. That puts on this group, SO3H. The reagent to do that is sulfuric acid, but it says fuming sulfuric acid. So typically sulfuric acid has the highest sort of weight content of all these mineral acids, so it's typically 98% sulfuric acid, 2% water. Even though it's strong, it's not strong enough to do the reaction, so fuming just means that they've bubbled SO3 into it. So it has sulfur trioxide gas bubbled into it. Then nitration installs the nitro group, NO2. Nitric acid itself is not strong enough, so it's typically run in the presence of sulfuric acid. So these classical conditions overall we say are pretty harsh, meaning that the starting material can't have a lot of other stuff in it because these reagents will basically chew it up or react with it. So those are basically the conditions. So we take a benzene, we can make chlorobenzene. So again, later on, I'll tell you that the how in which the mechanism occurs, but for right now, we just want to know what are the conditions necessary. And just to point out again, when we start with benzene, it doesn't matter which H gets substituted because they're all the same. But now when we have a mono-substituted benzene, if we did a uniqueness test, we could say those hydrogens are a set, they're equivalent. Those are a set, they're equivalent. And then that's its own set. So if we were starting with that and we wanted to do a second chlorination, where is it going to go? And again, that gets back to the induction and resonance. So that's really where the, once you know the conditions to get something on the ring, the intuition is in developing a strategy to control the positions of any subsequent reactions. So here's our benzene H. We can treat it with chlorine, aluminum trichloride, and now we have chlorobenzene. So the halogens, again, are a little bit weird in terms of categorizing them as electron donating or withdrawing. And what I mean by that, we know that chlorine is going to have 3 lone pairs, so it's delta minus, and that carbon would be delta plus. So by induction, it should be withdrawing. But due to the lone pairs, it's donating to some extent. So that makes it an electron donating group. So hydrogen for bromine, Br2, iron tribromide, we get a bromine in there. What I want to point out, kind of as a nugget of information here, we remember from organic 1, bromine's typically a good leaving group for SN2, but in this scenario, it's bonded to an sp2 hybridized carbon. Remember, those do not participate in SN2 reactions based on how the mechanism occurs with the trajectory of the nucleophile at 180 degrees from the leaving group, that argument. So even though you have a bromine on there, it's not a good leaving group. So here's a question where we're taking benzene, we're treating it with some electrophile that's a halogen to get a monosubstituted benzene. Then you're given the mass spec data. There's kind of two ways you can figure out the answer for this. One of them is visually, the other is numerically. And so basically we want to know what conditions were used. Does anyone have a first guess? Give you a clue here. So we have those two numbers there, and I'm old, so I can't read them on my screen. So one says, the first one is 156, the second one is 158. What is the ratio of intensities? Huh? 1 to 1. So do you remember what halogen that corresponds to in terms of a natural abundance? Let me twist the screwdriver a little bit more. I won't answer it just yet. If this is C6H6, this is C6H5X. Why don't you get out your calculators real quick? How much mass is C6H5? So what's 156 minus 77? So what is x? What? A little louder. Not only can I can't see, I'm a little hard of hearing. Bromine. So x has to be bromine. So that's the mathematical way you could do that. Or the visual way is bromine has two natural isotopes, bromine 79 and 81, that occur in a 1-to-1 ratio. So this 156 has bromine 79. The 158 has bromine 81 due to the isotopes. So now that we know X, what reagent was used, we have these two choices that have bromine in it. And this is where, like on your final exam, you're going to have to use the intuition about the nature of the mechanism that's happening. Sodium bromide has Br minus. And so minus can't accept electrons because it's already the anion. In molecular bromine, that's now electrophilic because the benzene ring is supplying the electrons. It supplies those electrons to bond to one of those bromines. You break the bromine-bromine bond, and then the reaction proceeds. In Br minus, that can't accept electrons from the ring because it's already happy. So as we learn all these reactions, you might see the same element and think, well, hey, it's got to be that. But again, the nature of the reagent needs to jive with the mechanism that's happening. Backtrack. Just as a review, if Cl2 plus the Lewis acid was used, obviously the masses would then be different. You could go through this exercise. You would add 77 plus 35, you would get a different mass. But then this ratio would be different. What would the heights be? Do you remember for chlorine?
2-to-1.
3-to-1? So we'll just jot that down. So again, there's a lot of ways that you can, arrive at the right answer. If you remember these kind of little tips, that'll relieve the mental burden a little bit. I guess. So the next reaction is sulfonation. And so this is installing an SO3H group. So benzene will become benzene sulfonic acid. So we all know sulfuric acid, H2SO4. Again, it comes in a glass bottle. Looks like water, but it's not water. It's a little more viscous than water. It's a pretty strong acid. The sulfonic acid is just an organic derivative. We've substituted an OH group, and then we've put this organic group on there. So sulfonic acids in organic chemistry are used for many purposes. They have a weaker pKa value. They're a little bit less acidic. But also the presence of that organic part will make it soluble in organic solvents. So it says the first pKa for sulfuric acid is -9. That substitution of OH for a ring, that moves it to -1. And since it's the pKa scale, remember it's a log scale, so it's 10 to the 8 difference. So if we were ranking benzene versus benzene sulfonic acid, really looking at the nature of the H versus the SO3H, how does that group affect the reactivity of the ring? Huh? So sulfur is a little weird because normally when you think like a heteroatom, there's a lone pair of electrons on it, but count the bonds to sulfur. It's way more than we're used to seeing, like 4 is the max, right? Because sulfur, it's below oxygen. And once you move from period 2 to 3, these elements have extra orbitals available to them, d orbitals. And then they can form these different bonding patterns and geometries that the period 2 can't. So these two double bonds, if we draw a resonance form for one of those double bonds, we'll see why it's electron withdrawing. So there's the lone pairs for oxygen. Notice sulfur doesn't have any lone pairs on it. If we break the pi bond, put the electrons on oxygen, the oxygen now becomes negative. The sulfur becomes positive. And since that element's in the benzylic position, it's positive, it then pulls electron density out of the ring. So because the ring is positive, if it were to undergo another substitution reaction, it's going to happen slower because those electrons can't get to the electrophile as easy. So as I said, ultimately what we're trying to do is understand the strategy by making benzenes with a lot of groups on them and controlling the relationships. Sometimes that can be pretty hard based on the natural reactivity pattern. And what we have to do is block a position. So we can put a group on there as a block, and then we can remove it. So you can remove a sulfonic acid group by using sort of the same conditions, but a little tweaking. To put it on, we have to use fuming sulfuric acid. We can take it off with really dilute sulfuric acid and water. And then we basically heat the crap out of it. So 100 degrees in the lab, like 100 degrees Celsius, that's hot. You're at the kind of verge of the safety limit, especially with acids. So we're cooking this up, and then we're basically removing that SO3H and then just replacing it back with the proton. So overall, again, I'm just showing you the conditions, but the strategy is we're going to use that to install it, do some other stuff, and then eventually remove it like it wasn't even there. And that's going to allow us to have a specific pattern of substituents. So we're kind of hopping around here. We got halogens on, we got sulfur, now we're going to go to nitrogen in terms of the classical conditions. And so for nitration, we're installing the NO2 group. And again, that was an electron withdrawing group. To do this, we need nitric acid in the presence of sulfuric acid, and we need really low temperatures. So there's a question here in blue. Why do we need sulfuric acid? So we have two acids in there. What's the deal? Because we already saw sulfuric acid can do its own sort of thing. In the presence of nitric acid, what favors formation of the nitro group? See. Okay. Just practically speaking, if the nitro group is NO2, nitric acid is HNO3. So we got to get rid of some stuff here. And the reason we use sulfuric acid is to help form the electrophile that's needed. So even though we're starting with two acids, one of them is going to be a base. So remember, the action of a base is to abstract a proton. From our knowledge of pKa, the smaller, more negative the pKa number, that means it's a stronger acid. So sulfuric acid is going to be an acid. Nitric acid is going to be a base. And then when we look at nitric acid, we have to get rid of an oxygen, right? So the way that I want to show this, see this OH here? I'm going to use one of those lone pairs as a base to abstract a hydrogen. So that's going to protonate that oxygen. So we've balanced our charges out. The oxygen of nitric acid is plus. It's balanced by the sulfate anion there, hydrogen sulfate anion negative. And so what this allows us to do is use the negative on this oxygen to do an elimination that will push out water, H2O. So now we have NO2. See how it's plus? That means it's electrophilic. The plus is still balanced by this negative charge. And so that's called the nitronium ion. So that's the electrophile for nitration. So just to point out, under these classical conditions, you can just take these two acids, mix them, it forms that. As I said, if you have a molecule with other sensitive functional groups, you don't really want to be exposing it to strong acids. NO2 plus is always nitronium. The nature of this counterion can change. So you can have different counterions. You can actually buy these commercially where these things are stable, and you don't have to go through this process of making it. You just buy it, you dope it into the reaction, and then you don't have any other concerns about the acid's going to chew up this part of the molecule. So I'll give one example of the mechanism. By and large, the arrow pushing is the same if we consider like the electrophile, the nitronium ion, can be any of those other things we've learned, like for the chlorination, the bromination, or sulfonylation. We have the electrophile. The ring itself is the nucleophile, so it's going to supply the electrons to form that bond. So we'll have the arrow coming out, pointing towards the electrophilic atom. We're going to form a CN bond, and then we'll push electrons that way so things get balanced out. If I can, let me point something out through drawing here. I want to draw this H next door, just so we see it's there. We already saw from expanding the nitro group that it has these charges, right, plus and minus, that are inherent to it. But we still need to keep track of this plus and this minus, because that hydrogen sulfate minus is still hanging around. Which means that we have to put that plus somewhere. So because I bonded the nitro group to that carbon has 4 bonds, meaning that the carbon next door has 3. So the plus charge has to be there. It's now electron deficient. So even though this is now negative and that's positive, again, the reason this does not attack that carbon is because the product would then not be aromatic. So the next step in this is an elimination. And the elimination of the hydrogen has to come from the carbon that got the new substituent. So this base will abstract that hydrogen so that these electrons can reform the pi bond. So I wanted to draw in this hydrogen to show you that's not being abstracted. So this comes around, abstracts that. The elimination then reforms that pi bond. So there's just some color to show you that what hydrogen has to be abstracted in terms of the arrow pushing. So overall, electrophilic aromatic substitution proceeds kind of stepwise through things we've seen. There's an addition. You get this high energy intermediate here that has to undergo an elimination. So addition, elimination overall results in substitution. Any questions? So as I said, this really can be generalized for any electrophile that we're using. We have to make sure that the benzene ring itself is matched to whatever that electrophile is. That's why we include Lewis acids and things. But there's an addition. Notice the carbon hybridization here. We start off as sp2. In the transition state, it's sp3 because it has 4 sigma bonds. And then the elimination restores that pi bond and gives us the aromaticity. So, back in the day, 1940s kind of era, these reactions were studied pretty extensively, and so this addition complex is known as a Meisenheimer complex. In terms of the reaction coordinate, you have something aromatic, product aromatic. This doesn't obey the rules for aromaticity because of that sp3 hybridization's breaking up the conjugation. So the driving force is to restore that. So pick your poison for whatever electrophile you want. These are the general arrow pushing for whatever is going to happen. So we got about 6 minutes left. I just want to introduce one further transformation, and then on Wednesday we'll talk about the implications of it. So we know how to get the nitro group on there. That installs a nitrogen. The nitrogen is in the nitro group. We know that that's electron withdrawing. So from the resonance forms, we saw that those 2 carbons were the ones that did not have the plus charge. So if you take nitrobenzene and you were to run another reaction on it, it's going to put the substituent where those red dots are. But we can do an inversion of that. We can count oxidation state of heteroatoms just like we do carbon. NO2 is highly oxidized. We can reduce it down to the amino group. So nitrobenzene to aniline, NH2. And we know that the amine will have a lone pair. And so now that's an electron donating group. From its resonance forms, we know that it can push a negative charge at those positions. So the specific relationships, starting from a substituent and then counting. A 1,3 is called meta. A 1,2 is called ortho. And a 1,4 is called para. So those are the terms used as directors. Whether the functional group's withdrawing, it's a meta director. If it's donating, it's an ortho para director. So the exact conditions to reduce that nitro, there's 3 of them shown. Tin dichloride and ethanol, hydrogen gas, palladium on charcoal and ethanol, or iron metal under acidic conditions followed by a basic workup. So no matter what to get nitrogen on, we have to do nitration. But if we don't like the reactivity pattern of nitro, we can reduce it to get a donating pattern. And then notice of this, what I haven't said yet is, you have 2 possibilities. Can it go ortho or can it go para? For the most part, things will go para just due to sterics. Like you want to get the next group as far away from the existing one. But ultimately, you do end up with mixtures. And so what we'll see is using NMR, specifically proton NMR, of the 3 scenarios, ortho, meta, and para, the proton NMRs are going to look very different based on the substitution patterns. And so that's when that uniqueness of sets comes in. So now that we know how to take NO2 to NH2, what we'll start with on, I guess we'll review that, but how can we then transform NH2 into those things we haven't seen yet? So fluorine, iodine, and oxygen, how do we get those on? And we have to start with that aniline to do that. So we'll look at that mechanism, we'll look at some data, and that'll allow us to figure out what group is actually going on there. Wednesday is